It's a pleasure to talk about the Geothermal Atlas, our new online tool that gives an overview about the potentials and also possible limitations for shallow geothermal energy use in Vienna. So I will tell you a little bit about the methodology that is behind the data calculation and also about the functionalities of the Geothermal Atlas. But before I do that, let's just think about why we are doing that. So what's the motivation for such kind of planning tools? First of all, we want to provide a harmonized databases, especially for planning, to accelerate the planning procedure. We want to increase the visibility of shallow geothermal energy. In Austria, we also have quite some applications already, but the awareness of this technology as a sustainable heating and cooling source is unfortunately still not very high. So we hope that we can increase the awareness with our tool. And last but not least, we also see a great benefit of such kind of planning tools or information systems to be integrated into a kind of a cyclic management process. That's what we thought about in a previous EU project. Where essentially we see that a lot of data is generated during the life cycle of such an individual geothermal system. In the planning phase, maybe also during the installation phase, during operating and especially in monitoring, a lot of data is generated. And this is very useful information that we can use for our resource data sets that we can then feed into the information system to be readily available again for the future planning procedures. And so this should also ensure that we have a sustainable and efficient use of our resources. And so we developed this tool mainly as a first step for Vienna. And before we go to Ireland, we might think about expanding it to the rest of Austria. But as I'm showing you this now for Vienna, I'll give a brief overview of the geology so that you know what we are dealing with here. So Vienna is located in the Viennese Basin, so we have sediments here. And in the upper part, we have a very productive shallow groundwater body that covers the eastern part of Vienna. This is the groundwater body called Machfeld Aquifer. It's Danube gravels, and it already hosts about 800 groundwater heat pumps that you can see here as the triangles that are used for heating and cooling. And some of them are only used for cooling. And then if we go further to the west, the hydrogeological situation gets a little bit more complex. We have some terraces here in this area, and then there are smaller streams coming in from the western part into the city, and they also have some smaller groundwater bodies attached to them. But the most information we have, or we had when we produced these data sets, they were readily available for this Machfeld groundwater body here. And so, yeah, I already mentioned the groundwater heat pumps. They are very important, not only in Vienna, but also in the rest of Austria. And second important technology regarding shallow geothermal energy are the borehole heat exchangers. And so that's the two technologies that we focus on in this Geothermal Atlas. You see here in the landing page, we provide geodata. So these are our different geological and also limits of use data sets. And then we have for the borehole heat exchangers, a site-specific potential calculation tool that I also want to show you. And to demonstrate, yeah, who are the target groups? Also maybe worth mentioning here. We have, as I already said, planners as target group. They can use the information that we provide in their specific dimensioning of the individual installations. Then we count homeowners and investors to our target groups. They can take a closer look to their properties that they are interested in or that they are owning to find out about the general feasibility of shallow geothermal energy at these locations. And then specifically this potential calculation tool can also be useful for educators and students because you can really play around with different borehole heat exchanger configurations to see how the underground data, but also the operational data changes the output of the borehole heat exchanger field. And then we also include the general public. And now I want to show you the different functionalities based on two examples. Example one is a virtual family called Waterhouse, and they want to know if a groundwater heat pump is generally feasible for their house. So they go to the geodata part for the groundwater heat pumps, and the first thing that comes up is our so-called traffic light map. It shows possible limitations for the groundwater heat pumps in three categories. One saying the use is generally possible. Yellow means more information is necessary, and pink means that the use is generally not possible. So the data behind this is, for example, protection areas. We have nature or landscape protection areas. They are here represented in yellow mostly, and then water protection areas with the highest priority indicating the pink colors. In general, we say that these limitations are not do not affect the resources itself. So we see this independently from one another. The only thing we did here for this traffic light map for the groundwater heat pumps was to cut it to the suitable groundwater bodies. So that's why it does not cover the whole city of Austria. All right, so that's the first start, and then we can go further into the different resource layers in this map viewer. So let's get started with the outline of the suitable groundwater bodies. You now already know that the majority here in the eastern part is covered by a very productive groundwater body, and to the west we have groundwater bodies with local or lower groundwater availability. And in this area, we could also not quantify the energy resources because the data was not available. But for this other very productive aquifer, we derived a lot of data sets, one of them being the depth to water level, taken from the ground surface down to the water level. This was already available as contour lines to us. And the groundwater basis was also available from a previous project done by a company commissioned by the municipality of Vienna. They did a 3D modeling of the shallower aquifers. And so that's why we got this information here. And with that, we could derive the groundwater thickness. So now you see that we have, especially here in the southern part, groundwater thickness of up to 40 meters. Another important information is the hydraulic conductivity. This was taken from numerical 3D models and also from a database of pumping tests, where we collected from different companies the pumping tests and derived the hydraulic conductivity. And where there were still data gaps, we also included data from the literature to come up with this hydraulic conductivity dataset. And then we have the groundwater temperature, where from around a little bit more than 200 observation wells, we had timelines recording the groundwater temperature. And then we selected two representative dates for a maximum and a minimum groundwater temperature for the year 2020 and interpolated those maximum, minimum, and mean temperature maps. So this is really the hydrogeological basis for the next calculations of the pumping rate. So this could only be done in the areas where we had all information available. And we used Team's well equation with a distance of 50 meters between extraction and injection well, and then calculated the pumping rate. And then if you take the groundwater temperature into consideration as well, combine it with the pumping rate, then you get the thermal power. And it's no surprise to see that in this southern area where you have a high groundwater thickness, the thermal power is also the highest. And then we also took the energy that is stored within the aquifer and included heat transfer from above and below to calculate the annual energy yield for two operation modes. The first one is mainly heating according to the climate that we have here in Vienna. And the second one is a balanced mode, meaning that you have used this for heating and cooling at the same amount. Yeah, so that was a lot of numbers, and maybe you already forgot with what I started with. And so that's what the experience of at least a family waterhouse is. So many different layers. But luckily, if you just click on any location, you get this text that tells you all the values of all the different parameters that I just mentioned here in this text, and also includes the different possible limitations and other important information here. So at this location, we see that the pumping rate is, for example, 4 liters per second. It's located in this productive aquifer. Looks good, so the family can go get a planner to further pursue their endeavor to get a groundwater heat pump for the house. So let's see for the second example, a planner commissioned by the Hotel Sunshine, and they want to know if the hotel can cover their heating and cooling demand with borehole heat exchangers. So we start again with this geodata. Here we have again this so-called traffic light map showing the possible limitations. Now you see that the whole city of Vienna is covered with this traffic light map. This means that we have here in Vienna a very good general possibility to use the borehole heat exchangers. And in yellow, again, we have some mainly landscape protection areas. And again, we have a couple of geological data sets that are indicators for the resources for borehole heat exchangers. Starting with the surface temperature, land surface temperature. This was taken by a European-wide published data set. They derived the data from satellite information. Taking the surface temperature into account and also groundwater temperature, we calculated the underground temperature. So where it was possible, we used the groundwater temperature, and additionally, we included temperature profiles that were taken during thermal response tests. That were not that many, I think around 10, something like that, thermal response tests were available at this time for the city. And from that, we more or less clustered the city according to those temperature profiles and included this in the calculation for the underground temperature. So we calculated actually the mean value for example for 100 meters. Then we have the thermal conductivity. If you look at the values here, you see this is not much of a difference. So the thermal conductivity in Vienna in this first 100 meters, you can say it's about 2. We can differentiate it a little bit in more detail due to the high number of boreholes that we took into consideration here that were a little bit more, a couple of hundreds, I would say. And we use the borehole profiles, so this represents purely the conductive thermal conductivity. No groundwater flow was included in the calculation here. And then it gets a little bit complicated because as of now, we only had geological data. But if you also want to know the energy and power of the borehole heat exchangers, you also have to take into consideration the operation and the configuration of the boreholes themselves, because the heat extraction rate strongly depends on the depth of the boreholes, on the distance between the boreholes, on the operation mode, the operating hours. And so if you want to calculate this heat extraction rate, you have to fix those operating parameters. And that's what we did. So we also distinguish here between the two modes again, mainly heating and storage. And for the extraction rate, we chose to go for one singular borehole to calculate the watts per meters. And then we did the same for the annual energy yields, also again for mainly heating and storage. And for that, we used two differently sized borehole heat exchanger fields. The method behind the calculation for these two parameters are the G functions, and we use the pi-G function published by Massimo Casasso. We use the pi-G function for this G function to calculate these values. And last but not least, the annual operating hours. I already said that this is also important to know, and this was derived from the surface temperature. So these are all static data sets. And again, when you go into the web viewer, click on any location, here in this case, the Hotel Sunshine, you get all the values of these different parameters summarized in this text report. So that's interesting data, but what about the potentials of individual applications? And we wanted to address that because we know giving such static data sets provides a certain limitation. And to provide this, we developed this site-specific potential calculation tool. And if you click on any location, then this happens, and magically a high number of boreholes appear. And they are just thrown in there based on whether this is a free space or not. If a building is there, then no boreholes are placed here. But now the fun starts because you can adapt this first borehole heat exchanger field. So you can play here around, change the distance between the boreholes, the borehole depth. You can decide what kind of heating system you have to go for the inlet temperature of the heating system. And then you have to provide annual operating hours for heating and for cooling. That's necessary information. And if you plug this all in, then you can already hit start and get a first overview about how much energy is available with this borehole heat exchanger field. And then you see this in a energy flow diagram. We have the cooling side of the building here on the left and the heating side of the building on the right. And in between is our borehole heat exchanger field. And you see how much energy comes in from cooling. Then we have here the part of energy that comes from the surrounding underground. And then this is how much energy you can take out for heating. But if you already know how much energy you need for heating and cooling, you can also plug in here your demand for heating and cooling. Hit start again, and then you would see if your demand is covered or not. And you can see this, for example, here in this flow diagram. We see that there is actually a lot of potential for heating and for cooling available. So this tells us that this borehole heat exchanger field is too big. Actually, you don't need that many boreholes, so you can go back and also maybe get rid of this random distribution of the borehole heat exchangers to get a more nicely aligned borehole heat exchanger field like this one. And yeah, can check out if the demand is covered maybe by this. And if you want to get a little bit more information than just this energy flow diagram, you can download a PDF report that summarizes also everything that you put in here. So you have a nice documentation of the calculation that you did. And then this also indicates that when you, for example, have a very unbalanced use here, it shows an example of how much energy would be actually available if you use the borehole heat exchanger field as a storage. So with this, we want to emphasize that you can use more energy when you use the borehole heat exchanger field as a storage. Yep, with that, you can also go further into the planning. And what I wanted to address here specifically is also that this is all written in German now, but please don't be intimidated because the browsers, they already can do a decent translation into English. We checked, so it should be okay that you should be able to use this also in English if you want to try it out. The PDF report is not translated to English, unfortunately, but if you're interested, I'm sure you will find ways to translate that as well. Yeah, with that, I'm already coming to the end and just talk a little bit about our next steps. As of now, we have this high data resolution only available for Vienna. We're working on it to expand it to further federal states like Salzburg and Lower Austria. And then we also want to offer this site-specific calculation tool for the groundwater heat pumps. That's also under development at the moment. And then we will start for Vienna with integrating automatically information from outside. So for example, from authorities like the groundwater protection areas, you know, they can change, and also the existing water rights, they are highly adaptable, or they will change over time. So it would be important of them that we can include them automatically. So whenever this data set is updated, for example, the traffic light map is updated as well. So that's what we want to implement here to offer really as much information about the that you need for planning of shallow geothermal energy systems. Yeah, last but not least, here's the link. Feel free to try it out. And then at the end, I want to emphasize that we do not want to replace any detailed system design. It is just intended as a for a pre-feasibility study. And also feedback is welcome if you try it out and feel like there are some bugs or anything you want to explain more or whatever. Let us know and send me an email.